Hello students, welcome to Narayan College online classes. In the previous episode we completed the batteries, the primary cells and the secondary cells. Examples. Primary cells mean the cell which cannot be recharged. Secondary cells simply the cells which can be recharged we are calling as a secondary cells. Already discussed the anode reaction, cathode reaction, overall reaction and all. Just it is a one table with a glance only. It is very useful for the revision purpose only. Let us see this here. Cell, cathode, and anode, electrolyte, and the cell reaction. You know, cell reaction takes place in anode and what? Cathode only. So, the first example we have dry cell. So, in the dry cell, graphite is a cathode, and anode is what? Zinc only. What is the electrolyte we are taking? We are taking electrolyte here NaO2 plus carbon. That is carbon electrode only. These act touching as a cathode, ammonium chloride, zinc chloride that can act touching as a anode only. We are calling as a moist paste of ammonium chloride and ZnCl2 you are taking in that dry cell. Now here the reaction takes place with the cathode and anode. Anode zinc and oxidation. So Zn converted to Zn plus 2 by loss of electrons, and cathode MnO2 gain H plus ions and electrons it will form MnOH and what here ammonia will form. Detailed discussion. Okay, next one we have mercury cell. So these two examples are what? Primary cells. In the mercury cell you are taking HCO plus carbon you are taking as a cathode, and zinc amalgam taken as an anode. The electrolyte is what? Paste of KOH and the ZnO. Reaction takes place in the anode. Zinc gain, okay, zinc combined with OH minus ions from the electrolyte. It will form ZnO, and at cathode this mercury oxide will gain electrons and water that will form HGO only. You know the overall reaction. Okay. And the next one we have lead storage battery. Lead storage battery is example for the secondary cell only. So what is cathode here? Lead is packed with the PbO2, and anode is what? Lead only. What is electrolyte here? 38% of sulfuric acid solution acts as an electrolyte. And you can see the reactions at cathode and anode. And anode lead, okay, combined with SO4 minus 2 ions, it will form a PbSO4 by loss of 2 electrons. And cathode PbO will combine with SO4 minus 1 H plus ions, it will form PbSO4 only. So these are the reactions that will take place in what? Lead storage battery. The next one we have, last one we have nickel cadmium cell. In this nickel cadmium cell, cathode is NaO2 and anode is what? Okay, we have cadmium only. So electrolyte is what here? KOH solution and electrolyte only. So the cell reaction you can say anode cadmium combined with OH minus ions from the electrolyte, it will form cadmium hydroxide. And you can see here NaO2 plus combined with water and it will form nickel hydroxide only. So these are the reactions takes place in the anode and what here? Cathode only. So this table is very important. Mainly in the board exams and all, they asking anode reaction, cathode reaction. Sometimes in the object exam they asking, okay, what is the electrolyte solution you are using, or which one used as a cathode and which one used as a anode only. Clear? So this is regarding about what? Primary cells and what here? Secondary cells. So dry cell and mercury cell example for the primary cell. Lead storage battery, nickel cadmium cell example for what? Secondary cells. See the next concept we have fuel cells. So what are the fuel cell means? Fuel cell or galvanic cell in which the energy of combustion of the fuels like hydrogen, methane and methanol is directly converted into electrical energy. We want to combust the fuels like H2 and methane and methanol, that gives directly what? Electrical energy only. So this is the process which takes place in what here? Fuel cells only. So generally what are the advantages of these fuel cells when compared to the normal generation of the electricity only? So electricity can be produced by the burning of the coal, burning of the gases, or electricity produced from the hydroelectric stations only. If the electricity getting from the thermal power stations, in that what the process takes place, by burning the coal they can produce the steam. By using that steam they can rotate the generators and they produce electricity only. But the thermal power stations, by burning of the coal, it will release lot of pollutants in the atmosphere, so it will produce more pollution, okay, into the atmosphere only. So this method, okay, will create what here production of electrical energy. During this production of electrical energy, some pollutants are combined with the atmosphere. Like if you are taking the gases also, process same only. In the gases, what you are doing, the gas can be burning, and that burning by using that energy will produce what is steam only. By using that steam, we can rotate the turbines. The turbines will generate electricity only. So the burning of the gases also produce a lot of the pollutants in the atmosphere. So this is also not an advantage method to prepare electricity. Okay, from what we are burning of the gas. Come to the hydroelectric stations. So hydroelectric stations, you know already, we can produce the electricity. How we are producing means the water can be sent into this water here turbines. So the turbine will rotate the generators, and the generators will produce electricity. But in the 365 days, we cannot produce electricity from the hydroelectric stations because the water is not available. Means they are not useful for the generation of electricity. But we'll come to the next. We have the fuel cells only. So in these fuel cells are what is the advantage means here we have to prepare the electrical energy without any pollutants only. Without any pollutants, simply we can burning the fuels. That burning of the fuels directly convert into what here electrical energy. So these are more efficient. So generally we produce, generally we want to prepare 100% of efficiency of electricity. Maybe you are getting a 70 to 80% of electrical efficiency from the fuel cell only. If you take the general methods, if you take the general process now, what we are getting, we have to get up to 40% of the efficiency of the production of electricity only. So this is one of the advantages of fuel cells only. So by burning of the fuels like H2 and methane and methanol, so they directly produce what my electrical energy. So this is regarding about the fuel cells only. So generally you can see that here galvanic cells we are using only. Galvanic cells we are using only. So generally you know this galvanic cell. You know the galvanic cell we have. What do you take, man? We have to take the half of the off cell and half of the oxidation cell and half of the reduction of the cell, and both are connected with a solid bridge. Just I am drawing a rough diagram for this galvanic cell. Okay, galvanic cell comes on over here, galvanic cell comes on over here, electrochemical cell only. So here we have to take these two compartments. One is the oxidation of the half cell and one is the reduction of the half cell only. So suppose they are taking a zinc rod can be kept in zinc sulfate solution. Here copper rod can be kept in what ma? Copper sulfate solution. This is, you know, this is a solid bridge. This construction now you know. Okay, but here what you are doing means here, if you take the galvanic cell, generally this is the construction only. But come to this fuel cell, the fuel cell, okay, cannot like a galvanic cell only. So here what will happen here, in the galvanic cell, already we are taking what ma? Already we are taking the reactants in the compartments only. Then we will carry out the chemical reaction. Then we will carry out the chemical reaction. But in case of fuel cell, what I am sending means here, we have to pass the reactants and we can remove the products simultaneously. Suppose you are passing the reactants here, products are produced, they can remove simultaneously. Okay, so whenever these reactants are passed to this one, once the chemical reaction takes place, the products are coming out slowly. So the products are removing simultaneously by passing reactants. Okay, but in case of galvanic cell, what you are taking? We are taking already the reactant in a one beaker only, and they can kept it and we are doing the chemical reaction. But in this case of fuel cell, what I am telling, the reactants are sent simultaneously and the products are removing simultaneously only. So this is the difference we are observing in case of what fuel cell when compared to what here galvanic cells only. Clear? So this is the difference between there is a small difference is there in this construction of the galvanic cell while it is working as a fuel cell. So the best example for this fuel cell is H2O2 fuel cell. H2O2 fuel cell. What it is? H2O2 fuel cell. So this is very example for which one here? This is example for what here fuel cell only. So we will see just first the construction, then we will see the anode reaction, cathode reaction. Then we can see, we will discuss the how the construction of this H2O2 fuel cell. Let us see this H2O2 fuel cell only. So in this H2O2 fuel cell, okay, we have to take the compartments. In these compartments, we are passing simultaneously H2 gas over here, O2 gas only. And here we can use the electrodes only. These electrodes may be platinum or palladium. We can use the electrodes only. Okay, and two sides you are taking. Two sides in the sense, you know, anode and what here, cathode you are taking only. So this is two electrodes only. These are getting maybe platinum electrodes or palladium electrodes you are taking here. Here we are passing what gas? H2 gas, and in this compartment you are passing hydrogen gas only. In this you are taking an electrolytic solution only. So the electrolytic solution in this you can take here aqueous NaOH or aqueous KOH you are taking. So electrolytic solution what you have to take? Aqueous KOH or you can take aqueous NaOH only. Here what is coming outside means here water is coming outside in the compartment only. So here these are the electrolytes only. So these are electrodes you are taking. One is what here? Anode, and one is what here? Cathode. So this is what here. This is the diagram for which one? H2O2 their cell only. So in this we have to observe what is the axis over here, anode and what here cathode only. So anode means here negative compartment, here cathode what here positive compartment. So this is the construction of which one? This is the construction of which one? H2O2 fuel cell only. So these are the electrodes only. So these are the electrodes only. What are the electrodes you can take here? Platinum or palladium electrodes are there. One is axis and anode and one is axis what here? Cathode only. So in this what we have to observe here. So generally we have to pass H2 and O2 gases bubble through this electrolytic solution only. Here we are sending what here? H2 gas, and here we can sending what here? O2 gas only. H2 and O2 gas can be bubbled through this electrolytic solution only. Here what happens means here this H2 can act as a fuel only. What is the role of H2? H2 acts as a fuel element. Okay, so this is the H2 role of it. And one more we have this oxygen also there. So in this H2 acts as what here? Fuel only. O2 acts as what here? Oxidizing agent only. So all the construction can discuss already told here. H2 and O2 gas is bubbled to the electrolytic solution only. I already told you whenever the H2 gas is coming to this one, then what happens here? There is a chemical reaction takes place between H2 and O2. They will produce what? Water as a product only. So in this production, what you can observe here? In this production, some amount of electrical energy water produced only. That we can identify by using what here? Voltmeter. Okay, this one, how much energy or how much electricity can be produced during this reaction? H2 and O2 both are combined to produce what here? Water only. So H2 acts as what here? Fuel. O2 acts as what here? Oxidizing agent. So what is the role of this electrode means here? These electrodes can increase the rate of reaction. Okay, now guess you can say the reaction can be takes place at what here? Anode and cathode. So we are observing the reaction at anode. So generally what you take here, what is axis and anode here? H2 gas is there. This H2 gas will combine with what ions means here? This H2 gas will combine with the electrolytic solution here. So what are the electrolytic solution we have? The electrolytic solution is NaOH or what? KOH only. So it will combine with the OH minus. Then what is formed here? We can produce water in the reaction. Water in the reaction. And here by loss of 4 electrons, you can balance this one here. 2H2 plus 2OH minus. You can take what will get here? 2 into 4 here. What will get here? 4 plus 4OH minus. You can take here. 2H2 plus 4OH minus gives rise to what here? 4H2O by loss of what here? 2 electrons. So here 2 hydrogens are there, going into 4 here, 4 plus 4 here, 4 into 2, 8 and hydrogens are there. Total. Oxygens over here, there are 4O and here also 4O. Now we can see the reaction at what? Cathode. What is cathode here? We are taking oxygen as O2. O2 acts what here? Cathode only. This O2 will combine with what? Water molecules. And again here electrons, it is converted into what here? 4OH minus only. You can write here 2H2O, here 2 into 4. 4 hydrogens are there here. And here O2 and here 2 O2 plus 2, 4 only here. So this is the reaction at what? Cathode. Now we can see the overall reaction means. So what is the overall reaction here? You can write here 2H2 plus 4OH minus gives rise to 4H2O by loss of 4 electrons, and here O2 plus 2H2O gain 4 electrons convert into 4OH minus here. 4OH minus 4OH minus and 4 electrons are cancelled, and here 2H2 plus O2. Here H2O is there. Here how many moles of H2O we have? 2 moles. Over here how many moles? 4 moles here. It gives rise to 2 moles of H2O. So this is the chemical reaction takes place at what? during H2O2 fuel cell. This is the chemical reaction takes place. So during this chemical reaction, what we are produced here, some amount of electricity will be produced in this reaction. That electricity we have to identify by burning of the H2O2 fuels. Okay, then we have to get formation of H2O. In this formation of H2O, then what will happen here? Some amount of electricity can be generated only. So this is regarding the fuel cell. That is example what I told here, H2O2 fuel cell. Also see the process here. H2 and O2 gas are broken through a porous carbon electrode into concentrated NaOH and KOH. So here what we are using at least like platinum or palladium incorporated as an electrolyte for increasing the rate of reaction only. You can see here oxygen here O2 generally acts as what is oxidizing agent. Oxidizing agent means it undergo what here reduction only. Hydrogen is oxidized, it can act as what? Reducing agent only. So this is regarding about this one H2O2 fuel cell. I already told you. So this H2O2 fuel cell now efficiency nearly 70 to 80% is there, and when compared to the normal generation of electricity, they can produce how much means here some 40% of the efficiency for the requirement only. And one more, these are pollutants free only. Pollutant free only, so there is no pollutions can be created because of this fuel cell. So what is important? You can prepare this diagram and you can write the reaction at the anode and the cathode. So these are important regarding about the fuel cells. So the next concept, efficiency of the fuel cell. So already discussed what the fuel cell, how they are working. Now you can see the theoretical efficiency of the fuel cell can be calculated from delta H and the gives-free energy only. You see the relation, the theoretical efficiency of the fuel cell can be calculated from the enthalpy of the combustion. Enthalpy of the combustion means during the combustion how much energy produced in the reaction, delta H, and the useful work done, how much work done, that is delta Z. Is that means what here electricity produced by burning of the fuel, how much electricity can be produced, that we have to calculate in the form of efficiency of the fuel cells only. Efficiency of the fuel cell eta is equal to delta Z by delta H into 100. You know delta Z free energy change and delta H is what enthalpy change into 100. So this is the formula we are using to find out what efficiency of the fuel cell. What is the efficiency of the fuel cell? Efficiency of the fuel cell eta is equal to delta Z by delta H into 100. This is the formula we are using. Clear? So this is very important formula. How much energy will be released by using that energy, how much of electricity can be produced, that we can identify in the form of efficiency of the cell only. So the efficiency of the cell eta is equal to delta Z into delta H by 100. Let us receive one problem on this efficiency of the fuel cell only. They given here, for example, delta H for fuel cell has found to be delta H for fuel cell has found to be minus 285.5 kilojoule per mole, and theoretical voltage of the cell has found to be voltage of the cell has found to be 1.23 volts. 1.23 volts. They are asking here what is the efficiency of the cell. What is the efficiency of the cell they are asking. They given delta H, that is minus 285.5 kilojoule per mole, and the cell potential also given how much here 1.23 volts. They are asking what is the efficiency of the cell. Efficiency of the cell eta, you know what is the formula of eta. Eta is equal to what is the formula here? We have delta G by delta H into 100. Delta H already given, that is minus 285.5. This is kilojoule per mole, and E naught of the cell is given. We can find out here what delta Z can find out. Delta Z, that is, you can say that is standard Gibbs energy only. So delta Z generally what is the formula we have? minus ENF E naught cell. So Faraday 96487 E naught cell already given. How much we have? 1.23 volts only. How many electrons are changing this H2O fuel cell? The change in how many electrons we can take? 2 electrons only. That is n value minus 2 into this is 96487 into what are the E naught of the cell? This is 1.23 volts. So all these you can multiply. You will get it here minus 237 point. This is 39 kilojoule per mole. So this is delta Z. Clear? Next we can substitute the values. This formula, eta is equal to delta Z by delta H into what? 100 ohm. So eta is equal to what the delta Z value we have? Minus 285.5. This is kilojoule per mole. This is kilojoule per mole by delta Z value. So delta Z we have minus 237.39. This is kilojoule per mole by minus 285.5 kilojoule per mole into 100. This joule per mole, kilojoule per mole is cancelled. Negative cancelled. Eta is equal to 237.39 by 285.5 into 100. Now efficiency eta, how much? This is 83%. How much percent? 83% only. So by using this formula, you are finding efficiency of the fuel cell. Formula is important. Delta Z by delta H into 100. How can you find out delta Z? You know this expression. Delta Z naught is equal to minus n of E naught cell that we are discussing in the Gibbs free energy part. So that formula I am using here. By using that, I will find out efficiency of the cell. What is the efficiency of the cell? The efficiency of the cell is approximately 83%. Next concept, corrosion. Generally, day-to-day life, we can observe this example for the corrosion. Corrosion means simply, we can say like this: formation of the oxide layer on the surface of the metal. Formation of oxide layer on the surface of the metal. Why it is happened? Due to the metal will undergo oxidation. Metal undergo oxidation in the sense metal can lose electrons. It will form a metal ions only. That metal ions will combine with the moisture, or you can say atmospheric oxygen. They will form a metal oxide only. Corrosion is due to formation of metal oxide on the surface of the metal. In day-to-day life, we can observe this corrosion. If you want to take iron nail, you can kept it iron nail outside for a long time. Then what happened? There is some formation of the oxide layer can be formed on the surface of the iron. That we are calling it a rusting. A rusting of iron is example for we'll say for corrosion. If we take the copper vessels, if you take any copper article, if that copper article suppose kept it outside, then what happened here? Some green color layer can be formed on the surface of the copper. That is also because of that copper under oxidation, it will combine with the atmospheric oxygen to form a copper oxide layer. And the tarnishing of the silver articles. Silver articles initially they have more shining is there on the surface. You can kept it for the outside, and what happened? That silver will undergo oxidation, it will form silver ions. That silver ions will combine with atmospheric air or oxygen, it will form a silver oxide. So these are the general examples you can observe in day-to-day life how this corrosion will takes place. Here, on this process, what happened here? In this process, metals undergo oxidation. Means oxidation, already told you, by loss of electrons. It will combine with atmospheric oxygen. So metal oxide layer can be formed on the surface of the metal. So this is this we can observe in the form of which one? Corrosion. So in this part, what we have to discuss, what is the reason how the corrosion will be takes place on the metal surface, and what are the anode reaction, and what are the cathode reaction, and what is the overall reaction. How can you prevent what are the methods to prevent corrosion? You know, because of this corrosion, majority of the metals get be damaged. If you take the ships, and you can take the iron grills, so these can be undergo damage because of which one? Rusting of iron or formation of the oxide layer on the metal surface only. How can you prevent these metals? We'll discuss in the concept of corrosion. Now see the definition, simple definition. The formation of oxide layer on the surface of the metal. And what is formed here is from a metal oxide. One more definition. Corrosion is a process of determination of a metal as a result of its relation with air under air or water. That means we can take air environment from the surrounding area. So the corrosion is a process of the determination is what an oxidation of the metal as a result of its relation with air or it can take the water or from the environment surrounding by it. So this is the definition of here corrosion only. I am taking example here, rusting of iron. Already here rusting of iron. One more here, formation of green color layer on surface of copper, and one more I told you tarnishing of silver. So these are the examples for corrosion. Take the first example here, rusting of iron. Rusting of iron means formation of oxide layer, means iron oxide, how the iron oxide is formed because of this corrosion will be discussed. So here you can see this diagram here. This is the metal surface. This is the metal surface only. Here what are the metal I took here? I want to take iron metal only. This iron metal will undergo oxidation. Iron I am taking here. Iron undergo oxidation. How the iron undergo oxidation? Iron undergo oxidation by loss of electrons. By loss of electrons. So how many electrons can be lost by iron here? 2 electrons are lost here. Iron lost 2 electrons converted into Fe plus 2 ion. Here iron loss again. Okay, same iron. We are taking 2 moles of iron. Suppose I am taking 2 moles of iron. I will get it 2 Fe plus 2, and here I will get it 4 electrons. So this 2 iron, okay, give how many electrons? 4 electrons. Here iron is converted into what here? Fe plus 2, that is ferrous ion. So here also iron converted into Fe plus 2 ion. So these give how many electrons means? So these combined or these together they give 4 electrons. These 4 electrons can be absorbed by the moisture. Moisture contains water, or you can take here oxygen is there. So these 4 electrons can be absorbed by the moisture. Oxygen and H plus ion with 4 electrons, it gives rise to what here? Water. It gives rise to what? Water only. So this oxygen, okay, what is there? It will combine with what here? Fe plus 2 ions. It will form what here? Fe2O3 form. That we can call as iron oxide layer or oxide layer formation on the surface of the metal. So this is a diagram position. Here iron metal undergo oxidation, it is an anodic spot. What's what it is? It is an anodic spot only. So iron undergo oxidation produces an anodic spot. That electrons can be taken by the H plus will combine with here oxygen or it will form what here? Water only. So you can see here this Fe plus 2 ions. These Fe plus 2 ions, what are there? They again combine with oxygen. They will form what here? Fe2O3. Generally we are calling as it is a rust only. Okay, so the rust how can be formed means here the rust can be formed by this iron Fe plus 2 ions are combined with moisture or can say oxygen. What is formed here? Fe2O3 formed. So this is the process which takes place during the formation of oxide layer on the surface of the metal. What is the metal I am taking here? I am taking as iron metal. So oxidation means generally oxidation can be taken place at what? Here anode only. So what is the anode reaction you get? Anode 2Fe converted to 2Fe plus 2 by loss of what here? 4 electrons. Now we can see the reaction at the cathode. At the cathode we have to see the reaction. So at cathode here what is the reaction will take place here? Here O2 is there, you can see this one. O2 will combine with what here? 4 H plus ions and 4 electrons. It is converted into 2H2O. Water is formed. Same reaction. This is anode reaction. This is what reaction? Cathode reaction only. So this is the cathode reaction. Now we can see the overall reaction. You can see. So what are the overall reaction? You can observe here. This overall reaction I want to take here combining these two. Then what I will get here? 2Fe. What is cancelled here? 4 electrons and 4 electrons are cancelled only. So 2Fe plus O2 plus 4H plus it gives rise to 2Fe plus 2 plus 2H2O. So this is the overall reaction that takes place during rusting of iron, or you can say formation of the oxide layer on the surface of the metal. So this is regarding about rusting of iron, important anode reaction, cathode reaction, and overall reaction. See this spot here, Fe plus 2 ions. These Fe plus 2 ions are there. These are further oxidized by dissolving oxide, atmosphere, or from air to form ferric oxide. This Fe plus 2 ions are there, is combined with O2 from the atmosphere or air. It will produce what here? Fe2O2, that we are calling is what? Ferric oxide. With further production of which one here? H plus ions only. How they produce H plus ions only? This Fe plus 2 ions are there. It will combine with oxygen and water. They will form ferric oxide Fe2O3 and they produce further H plus ions only. Now see the next point here. The ferric oxide then undergoes hydration. Whatever the ferric oxide is formed here, it undergoes hydration. Hydration in the sense combined with water, they will form hydrated form of oxide that we are calling as rust-O-Me. What is the formula of hydrated form of this Fe2O3 X6 we are calling as hydrated form of the oxide? That is the formula we are calling as Fe2O3 X6O. This we are calling as what? Rust-O-Me. What is the formula of the rust? The rust formula is Fe2O3 X6O. So these are the reactions can be takes place during rusting of iron. First one anode reaction, second one cathode reaction, third one overall reaction. How this iron can form ferric oxide? This ferric oxide is formed by the combination of Fe plus 2 O2 and H2. It will produce ferric oxide. That ferric oxide again combined with the water, they will form hydrated ferric oxide. That hydrated ferric oxide are calling is what? Rust. So this is regarding about which one? Rusting of iron. So the next one, methods used to prevent corrosion. The first method we have barrier production, sacrificial production, electrical production by using an anti-rust solution. These are the methods we can use to prevent the formation of the corrosion on the surface of the metal. So barrier production is there. So how can you use this barrier production? Means the barrier production can be used by painting the surface of the metal, by applying the grease or oil on the surface of the metal, by applying the chemicals like bisphenol. Okay, this is regarding about barrier production. The metal can be covered. Okay, what we do here? Metal surface can be covered by using the chemicals. We have to take here bisphenol. This is the chemical only. By applying this chemical on the surface of the metal. So one more here, by applying here oil or grease. Oil or grease you can use, and more metal we can do painting on. So whenever we can do the painting on the surface of the metal, what happens? It does not undergo oxidation, or it does not undergo formation of the oxide layer, because the layer will protect the metal. The metal does not undergo oxidation. There are three methods are there. The first method, apply by using bisphenol chemical, by applying this bisphenol chemical layer on the surface of the metal, and by applying oil or grease on the surface of the metal, and one more by applying the painting on the surface of the metal. So by using these three methods, we can prevent the corrosion only. So this is the first method. The first method comes under what here? Barrier production. Barrier production. See the next one we have sacrificial production. So sacrificial production means we have to add some metal layer on the surface of the metal which undergo oxidation. Means we are protecting the metal by applying some metal coating on the surface of the metal. Suppose I am taking iron metal. Iron metal undergo oxidation will form a Fe plus 2 ion. More chances are there the metal itself undergo oxidation only. How we are protecting this iron metal means I want to apply some zinc coating on the surface of the metal only. Whenever I want to apply I want to add some zinc coating on the surface of the iron metal, then which metal undergo first oxidation? Means zinc only undergo oxidation, iron does not undergo oxidation in that case. Means what here? By protecting the metal by applying one more metal on the surface of the layer, this we are calling as galvanization. What process? Galvanization. By adding one metal on the another metal. What are the one metal here? Zinc we are taking. We can add the zinc coating on what? Iron metal. From this what you can say, zinc undergo oxidation but iron does not undergo. By using this method what you can say, we can protect the formation of the oxide layer on the surface of the metal. This process generally we are calling as galvanization. So again you can see sacrificial production. In this method iron is protected from the rusting by covering with the layer of metal which is more active than iron. Already told you this is we are calling as a galvanization, okay? Covering of the one metal by other metal by adding some oxide metal layer on the another metal. So we are making here zinc composition for this covering of iron surface. So if you want to zinc, you can use the zinc. We are calling the process we are calling is what? Galvanization. Okay. Here. So I am taking zinc and iron, both I am taking. Zinc is we are taking, iron and also we are taking. And zinc undergo oxidation and iron undergo what here? Oxidation. You can see both zinc and iron get exposed to oxidation, but zinc undergo oxidation when compared to what? Iron. You can see Zn gives gain 2 electrons converted into zinc. This reduction potential for the zinc is minus 0.76, and Fe plus 2 gain 2 electrons converted into Fe. The reduction potential for iron is given minus 0.44 volts. When you can compare this reduction potential, what is the point over here? Reduction potential of zinc is less than what? Iron. Reduction potential of zinc is less than iron, so zinc can be oxidized easily when compared to the iron ore. By this method, what we make here, we want to cover the iron metal by surface of the zinc on the metal, iron metal only. So formation of the zinc layer on the iron layer. Then what happened here? Zinc only under oxidation. It cover the iron from what? Oxidation. So by this process, what you can say, we can cover the iron metal surface by adding a metal coating on surface. The process we are calling is what? Galvanization. So this comes under what here? This comes under sacrificial production. So what are you comparing? You are comparing the reduction potential. The reduction potential of zinc is less than the reduction potential of iron. So zinc undergo oxidation. So the next method, electrical production. So generally this method is used for the protecting iron articles from which they are contact with the water. If the iron particles can be contact with the water, generally where the iron particles contact with the water, we can see the water pipes. Water pipes and all, the water can be moved through the iron rods, iron what you can say, iron pipes only. So in that what you can see here, that is underground water pipes only. So if the iron metals can be used in contact with the water, what method we are using means we have to use the method electrical protection only. So these articles can be protected. How they are protected here? These articles can be connected with the active metals which are having low reduction potentials than iron. Okay, active metals which have lower reduction than what here? Iron. What are the active metals we have? We have zinc is there, metal magnesium is there, magnesium, iron. Sodium, potassium, magnesium, calcium, barium, aluminum. These are calling as active metals only. By using this metals, so these metals having a lower reduction potential, they can be added on the surface of the metal only. So we can see. So the articles are connected with the active metals which are having a lower reduction potential than the iron. They will lose electrons in preference to the iron. If you want to add a magnesium or the zinc, which one lose electron here? Magnesium will lose electron when compared to what here? Iron only. I take the magnesium as example. Mg plus 2 log gain 2 electrons converted to magnesium and Fe plus 2 converted to Fe. We are comparing the reduction potentials. The reduction potential of magnesium is less than what? Iron only. So magnesium is oxidized in preference to what here? Iron only. So what is oxidized here? Magnesium is what? Oxidized. Magnesium is oxidized than what? Iron. Because this magnesium is a more reactive metal which having lower reduction potential. So this is regarding the electrical production of the metal. The last method we have using a anti-rust solutions only. By using these anti-rust solutions, we can prevent the corrosion only. So you can see here, to prevent the corrosion, iron particles can be anti-rust solutions can be used. What is the example for this anti-rust solution is here? Alkaline potassium, or you can take alkaline chromate solution. Alkaline potassium phosphate or alkaline chromate solution you are taking, the iron article can be dipped in this alkaline phosphate solutions or alkaline chromate solution. Then what happened here, the iron articles can be dipped in anterior solution which is having some alkalinity that is basic in nature. That basic ions will remove the H plus ion from the solution. They can be prevented from what? Rusting only. So these are the methods used to what? Preventing rusting of the electrode. We discussed here 4 methods we are discussing. First one, barrel production, next sacrificial production, the third one we have electric production, and next one we have using anti-rust solutions only. So these are the methods we can use the prevention of which one? Corrosion. The electrochemistry completed. So what are the important topics you can observe in this concept means already give one flow chart, resistance, conductance, conductivity and all I gave it. The next one more flow chart we have electrochemical cell. Electrochemical cell convert chemical energy into electrical energy. Cathode is positive, anode is negative. In this electrochemical cell we are finding EMF of the cell, E naught cathode minus E naught anode, and E naught RH is right hand side minus left hand side. And one more for the electrode reaction we are writing Nernst equation. This is for this equation I am writing Mn plus gain n electrons converted into M, and E cell is equal to E naught cell minus RT by NF into Ln 1 by Mn plus concentration of the solid is always 1 we are taking. So for cell reactions given like this, AA plus PP gives rise to CC plus DD. In this case we are writing Nernst equation. E cell is equal to E naught of the cell minus 0.059 by N into log concentration of the C whole power C, concentration of the D whole power D by concentration of A whole power A into concentration of B whole power B. And one more formula we have, E naught cell is equal to 2.303 by 303 RT into NF by log K. This we are using in the form of equilibrium constant K only. So this is the relation between E naught of the cell and equilibrium constant. E naught cell is equal to 2.303 RT by NF into log K, or you can say E naught cell is equal to 0.059 by N into log K. See, already we did some of the problems on this two formulas. And one more we have Gibbs free energy and equilibrium constant E naught of the cell. Delta Z naught is equal to minus N of E naught cell, that is the Gibbs free energy formula. Or delta Z naught is equal to minus RT ln K by taking equilibrium constant, or delta Z naught is equal to minus 2.303 RT into log K. So these are the formulas we are using in electrochemistry, particularly by calculation of delta Z naught or E naught of the cell by giving equilibrium constant by using Nernst equation. So these are the concept map you have to keep in your mind for doing problems related in this electrochemical cell calculations. The one more concept we have discussed the Faraday's law of electrolysis. We have two laws are there, Faraday first law, Faraday second law. Now mass of the substance deposited at cathode during electrolysis directly proportional to quantity of electricity passed through the solution, that we are writing W is equal to Z into Q. What is Q? Q is equal to I into T. What is Z? Z is electrochemical equivalent. Already discussed about the formula of Z also. And one more second law of electrolysis. What you can say? If the same quantity of electricity can be passed to a different electrolytic solution, the mass is deposited at cathode is directly proportional to the equivalent weight of the substance. This is the expression of. And come to the next one, this is the cells or batteries only. Primary cell and secondary cell, we have two types of the cells are there. Primary cells not be chargeable, secondary cells can be chargeable. In the primary cells, electrode reactions cannot be reversed, but in case of secondary cells, electrode reactions can be reversed only. So what are the example for this primary cells? Dry cell and vacuum cell. And what are the example for the secondary cells? We have lead storage battery, nickel cadmium cell. Already I given one of the block diagram for the cell reaction, anode, cathode, and one more electrolyte. What are the reaction takes place at the anode and what are the reaction takes place at the cathode, and now we'll discuss it. Okay, so this is one of the block diagram for the representation of the cell and batteries, and for this is for what? Faraday's law of electrolysis only. So this is regarding about electrochemistry. In the next episode we will go for the objective questions on electrochemistry.